Hello everybody, my name is Abdullah Hadi. I'm going to talk about this paper on smart contract defined secondary control and co-simulation for smart solar inverters using blockchain technology. This presentation we prepared as following these contents. I will start with a short introduction, and then I'll talk about blockchain technology, and I will give a brief introduction to the smart contract, and then I will go to the our proposed system where we propose a smart contract defined control framework. I will also present the co-simulation platform that we used in this paper, and I'll finish our presentation by providing the validation of the simulation results as well as the conclusion. Smart inverters nowadays can be easily monitored and controlled from a remote location. It is very flexible for the user, but at the same time, it brings up the concern of cybersecurity. As we can easily access to these inverters, that means that any hacker can also get the access to these inverters and can manipulate any information as they want, which can be resulted in a big grid disturbances. Current grid monitoring system is also not fully vulnerable to cyber attack. So these problems can be solved using blockchain technology. That is what we are proposing in this paper, which is a distributed laser system. Can remove many of the concerns that we have in our current grid system. So in this paper we are proposing a blockchain assisted control framework to improve the security and the control of a smart inverter based microgrid system. A SCADA system basically consists of a central computer-based system, which is also connected to multiple remote location units and communicate using some wide area network links. This system has been extensively developed over the last few years, but still it composes many vulnerability to cyber attacks. For example, one of the big problem of this system is the single point of failure. It is easily breakable if any hacker can access to this master server, then the whole system can collapse easily. Another problem is the easy target for the physical attack. Anyone who has the access to this physical system can also do any kind of disturbances to this system. It is also very complex for the operators, which brings many concerns as well. It is expensive for a small scale islanded microgrid system because nowadays if we want to connect renewable energy sources to develop an isolated microgrid system, at the same time we want to control it using such kind of centralized or decentralized monitoring system, we cannot just apply the SCADA system because it also brings up a lot of cost for the system. Distributed laser technology in this case can solve many of these problems. As we know, there are many platforms that uses distributed laser technology. One of the platform is known as Bitcoin, which has been proven for its high security over the last 1 decade. There are many characteristics of distributed laser technology. Some major characteristics I have shown in this picture. It is inherently distributed. It is also anonymous, meaning that all participants that are connected to this blockchain network will be anonymous to each other. Any transactions that are made by each of these participants will be time stamped, meaning that we will be able to see exactly at what time each of these transactions were made. It is anonymous, it is immutable, it is highly secured, and finally, and most importantly, it is programmable. It is also referred as smart contracts. Using this programmability of the blockchain network, we can develop any secondary or tertiary level control for our microgrid application. On the right hand side of our slide, we shared a summary of this distributed ledger technology based microgrid control system. The remote terminal units can be referred as peer in this picture. Each of these peers consist of chain code or a smart contract. This chain code should be identical to all the peers as long as they are connected to one single channel or one single network. They also consist of ledger and world data, world state, which is mainly the log information of each of the transactions that is made by each of these peer as well as the other peers connected to this network. And finally, they are connected to server nodes. In this case, we are showing 4 server nodes. That can be any number of the server nodes that we want to develop. They are mainly developed based on a cluster system, meaning that any node can go down anytime without hampering the regular operation of the microgrid system. In this way, we can improve the resiliency of the microgrid system. We use Hyperledger Fabric platform to develop our blockchain network. This network has Fabric CA or Fabric Certificate Authority, which mainly provides the certificate to each of these clients as well as all the peers and ordering service connected to this network. Once these clients has their own certificates, then they are allowed to enroll into the network. After the successful enrollment, they become authorized client to initiate the transaction with this network. Now the transaction or the block is initiated from the client node. With the help of the peer node, this client sends the transaction information by executing the chain codes. After execution of the chain codes, the endorser peer endorse this transaction or validate the transactions. Once it is validated, then the orderer peer make the sequencing of the data, and this is how the block is created. Each blocks may consist multiple transactions depending on the size of the data that is transferred from one client to the other. A smart contract is an event-driven program that executes the terms of the contracts with the state, which run on a replicated shared blockchain ledger. This cannot be referred as one particular script. There are actually multiple scripts that make this whole smart contract. So we can say like a combination of several scripts can be referred as a smart contract of these systems. In this slide, we just shared one example of the script is also called as the chain code. In this script, we mainly define the participants, who are the participants of the network, what will be the asset of each of these participants, asset informations, also how we want to make the transactions for these assets, and finally what will be the event of these participants. There is another script which is a Java script called logic.js, is not shown in this slide. In that script, we mainly developed our logical statement to develop the secondary control system. So in this paper, we are presenting multiple inverters that are connected to a common grid system, as well as supplying power to local loads or the common loads. That these overall system are connected to a blockchain network where we have these peers connected as well as the ordering system. On top of this, we have the smart contracts where we mainly can develop our secondary or tertiary control or access control even for the monitoring system. These inverters are also consist of their own primary control system that mainly controlling the inverters. So in our case, we are mainly developing the secondary control in our smart contracts. In this secondary control, our main target is to set the active and reactive power set points according to the different conditions of the grid system. Now the primary control system are developed as two stages. We have a group control in the beginning while we are controlling the active and reactive power. That is also driving the voltage and current loop control. That is finally generating the reference signal to generate the pulse width modulation for each of the inverters. These are the mathematical equations that we used to develop both of these group and voltage and current loop control. The overall control structure are mainly shown in these pictures. Here we have the group control structure that is connected to the voltage control loop first, and then we are going through a current loop control to finally generate the reference signal for the PWM generator to finally control these inverters. Now we will see how we develop the secondary control system in our blockchain network. In the very beginning, our Simulink model mainly defines some parameters for each of these inverters. Inverter 1 collects the information for the DC bus voltage, active power set points, and the load demands. Similarly, the inverter 2 also collects the information of the DC bus voltage, active power set point, and the load demands. Once they collect this information, then we run some condition using these informations. The first conditions that we run is based on the availability of the inverters as well as the load demands. In this condition, our both inverters are available and the maximum load demand. So we want, if this condition is true, then we want to set our active power set points for both of the inverters as the maximum power capacity. If it is not true, then we want to go through another conditions whether it is true or not. The second condition is that both of the inverters are still available, but the load demand is now half. So in this condition, if it is true, then we want to set our active power set points for both of the inverters as half of their full capacity. The third condition is that one of the inverter is disabled to supply the power. In this case, we are considering the second inverter goes down and also the load demand remains the same as the second condition, which is the half load demand. In this case, we want to set our active power for first inverter as a maximum capacity, but the set points for the second inverter should go 0 as it is unavailable. If this condition is not true, then we just want to set the active power set point 0 for both of the cases, because we are considering both of them are unavailable. Once it is done, then the Simulink model again goes back to the input, and then the whole algorithm runs again. Co-simulation platform was the most challenging part of this research. We used two different pieces to develop this whole system. In PC1, we developed the Simulink model based on two inverters and a grid system. And second PC we used to develop our blockchain network. And for the communication between two computers, we used a function which was developed within the MATLAB Simulink model. And this function was designed based on three major steps. In the first step, we applied the sending transactions. In this step, we mainly use the HTTP post request to post the pset values, VDC values, and the load demand from the Simulink model to the blockchain network. In the second steps, we perform the updating transactions, which is mainly the result of the secondary controller, because in the secondary controller we check three different conditions and define what will be the updated set active power set values. This is done in this second steps. On the third step, we perform the receiving transactions using the HTTP GET request. So in these steps, our function from the MATLAB Simulink calls the updated pset values from the blockchain network in order to run the Simulink model using the updated active power set values for both of the inverters. And this is how we perform the communication between these two computers. This is the example of the function, the coding of the function that we developed within the MATLAB Simulink model in order to build this code simulation platform. So we manually created these three different conditions during the simulation. Here in this graph, we presented the result for the inverter 1 and inverter 2. These blue lines represents our manual triggering results as well as what should be the active power set value for each of the inverters. And the red line represents the results from the primary and the secondary control system. During the first condition, where we kept both of the inverter available and the load demand was the maximum, so both of the inverters should supply at its maximum capacity. That is what the inverter primary control and secondary control was doing. On the other hand, during the second conditions, both of our inverters are available, but we reduce the load demand as a half. So both of these inverter preset values should go half of its full capacity. In the third condition, this is the most interesting part. We removed one inverter. In this case, we removed inverter 2. So that means only inverter 1 is now available, but our load demand was same as it was for during the condition 2. So inverter 1 should support the load that the inverter 2 was supplying to. So the preset value for the inverter 1 should go to the maximum capacity, as the inverter 2 was down and was not in the network. So the overall results was showing exactly as it was expected from the secondary control system. So it again proves that we can apply this blockchain network technology in order to monitor and control our microgrid system based on PV or wind turbine. So in summary, in this paper we proposed smart contract defined secondary control for a smart inverter based microgrid system. To validate our proposed model, we introduced a co-simulation platform where we developed a MATLAB Simulink based simulation model in one computer. In another computer, we designed a blockchain network where we mainly developed the secondary control system. The result proved the effectiveness of the proposed model, as well as it proved that the resiliency can be improved by this way, and also it can reduce the risk of the single point failure, which is the main concern of the current SCADA system. Before finishing my presentation, I would like to acknowledge Department of Energy to support this project from the very beginning. And that's all in my presentation. Thank you very much for your attention.